Welcome back to Physics 141 Online. We're making the transition now into Chapter 6, and the topic's going to change. We've studied mechanics, which has to do with the connection between forces and the change in motion that those forces cause. Now we'll be looking at the same kind of problems, but through a slightly different perspective. And the quantities that we're going to define and make use of in this section, which covers both Chapter 6 and 7 in the textbook, are work, energy, and power. And here's the outline. Today I'll just be working through the first point, the definition of work and how we calculate it. Alright, work is defined in a colloquial sense in the English language to mean a variety of different things. Some sort of exertion is usually implied. But in physics, words like this have specific, well-defined meanings. And sometimes we can't really get the right idea about the physics meaning by just falling back on our common everyday meaning. For physics purposes, a constant force that acts on an object where the object is only moving along one direction, in one dimension, does an amount of work that can be expressed in the following way. And I'll show the equation in just a second. But first, you see that here's the object that's going to move a distance delta x along the x direction, and it's being pulled by a force F that's constant. But the force doesn't have to necessarily be along the direction of motion. It can be at an angle theta, as in this case. So the work done is equal to the component of the force vector along the direction of motion, which here is F sub x, times the displacement along the direction of motion, which is delta x. And here, the x component of the force vector is just given by F cosine of theta. That's the component of F that lies along the direction of delta x. Now, this only holds true for a constant force and for an object that's moving in just one dimension. We will get a more general definition in just a minute. The unit for work is the Newton meter, as you can see from this definition. It involves a force times a displacement, and we give the name joule to this special unit, which is the unit of work and the unit of energy as well. It's named after James Prescott Joule, who was a British scientist in the 1800s, in the 19th century, and he was one of the first people to do experiments that showed clear evidence for the equivalency between heat and work. And so heat and energy were not always regarded as being different manifestations of the same thing. Joule is the person responsible for showing that experimentally. Now there's more general definitions for work because we might have a situation where the force acting on an object, the object's still moving in one dimension, but where the force is not constant. It's not the same. It's changing somehow. We already know situations like this can happen with springs because the force exerted by a spring on an object depends on where the object is. The magnitude of the force changes as the spring is compressed or stretched. But here, just imagine in this sketch that we have a force F sub x that's changing as the object moves from x1 to x2. How do we find the work done here? And the key insight is that the work done for a small change delta x, we already have this first line as our definition, a small change delta x multiplied by the force acting at that point or over that interval is equal to the amount of work done. And if we make that delta x very, very small, if we imagine there being a very thin vertical strip in this diagram here, then the work done across that strip will be the value of the force times the width of that strip. And that's nothing more than the area of that strip. And so what that shows us is that the work done is the area under a force versus position graph. And the way that we can write that down mathematically using a special symbol is like this. We can imagine adding up all of the individual vertical bars, adding up the areas of those from x1 to x2. And the mathematical symbol that we use is called an integral sign. You have dealt with summations before. Summations add up many objects to get a total. And this is a special kind of summation because it adds up objects in the limit where they get very, very thin. So this tells us that the limit of the area of all of these thin rectangles added up together gives us the net work done. And the way we read this is we read this geometrically as the area underneath the force versus position curve. And reading this mathematically, in words we say that this is the integral, which means integral means the total, right? The sum. It's the integral of f of x from x1 to x2, and that represents the area under the curve. So once again, just to make it clear, hopefully, delta x in this equation up here means a finite displacement, one that is greater than 0 and significantly greater than 0 in some cases. Dx here, the delta has changed to a d to indicate that what we're doing is we're taking the area of very, very thin strips in the limit where they become so thin that they are almost vanishingly small. And the opposite of infinite is infinitesimal. So this is an infinitesimal displacement between 2 points in space. All right, now if you haven't come across this in your math classes yet, you will. This is the subject of integral calculus, and you will get there soon if you haven't seen it yet. All we're going to do in this course is teach some very simple methods for calculating the area under curves like that. Now graphically, if what I just said wasn't very clear, all right, imagine again that we have this force versus position graph, which is the solid line here, and the work done in moving from x1 to x2 is approximately the sum of these vertical rectangles. Of course, it's not exactly, the area is not exactly the sum of those rectangles because you have the little points up here where the rectangles don't completely fill in the space. And of course, there's some parts of the rectangles that lie above the line. So the areas of those shaded rectangles will only be approximately the same as the area under the curve. But we can make the approximation better and better by making more and more rectangles and making the individual rectangles thinner and thinner. So if delta x gets smaller and smaller, you can show mathematically that this approximation gets better and better, and that by adding up the areas of all the rectangles, as you make the width of the rectangles thinner and thinner, you'll get a better and better approximation to the true area underneath the curve. And the exact value for the work is indeed the area underneath the curve, which here is the gray shaded area. So, how do we do this? Right? If we know the equation for this force function, how do we find the area underneath that? And there are surprisingly pretty easy ways of doing that once you learn a little bit about integral calculus. So stay tuned, and I will show you in just a few minutes how to do that for particularly simple kinds of polynomial functions. But before we do the integral calculus, to show us how to calculate the work done by a changing force, let's go back to the case of a constant force, but now where the object is not just moving in one coordinate direction, but might be moving in x, y, and z directions at the same time. And so the way that we do this, instead of writing down f sub x times delta x, we use our knowledge of vectors, and we define a new quantity that's called the dot product of two vectors. So we take the force vector that's acting on an object, and we form this dot product of the force vector with the displacement vector, delta r. That's the displacement of the object from its initial point to its final point. Now how do we evaluate this? Well, we'll get there in just a second, but let me just also indicate that if the force in question is not constant, we take a similar kind of dot product, except we call it, instead of delta r, we call it dr, because it's a very, very small displacement, and then we have to add up this quantity from the initial point to the final point. That's what S1 and S2 represent, the initial and the final points. Now, the delta r, in this case, it serves the same purpose that delta x did for one-dimensional work, but this now is a displacement vector because it takes us from the initial to the final point along some direction in space. dr in the integral expression on the right-hand side means a very, very small displacement vector. And the answer that we get is exact for the work in the limiting case where that displacement vector becomes infinitesimally small. how do we evaluate this dot product, or as it's sometimes called in math textbooks, the scalar product of two vectors? How do we do that? Well, we just have to remember the definition of work. Work was defined, if you have a force acting on an object as it moves through a displacement, it's the component of the force lying along the displacement direction times the displacement. All right, so this represents that very idea. In words, it's written on the right-hand side. Mathematically, we have a compact notation on the left-hand side. So let's look at this for two general vectors, A and B. If we draw them tail to tail, and they are separated by an angle theta, then the dot product of the two, using this definition in words, is the component of A lying along B times the magnitude of B. And the component of A lying along B is A cosine theta. So this is A cosine theta B, and usually we write it as AB cosine theta. So A and B are both vectors, but this dot product of the two vectors is a scalar quantity. It's not a vector, and it simply has the magnitudes of the two vectors times the cosine of the angle between them. In component notation, let's say that you're given your two vectors A and B, not drawn in space with respect to a particular coordinate system, but we're rather told that A is something times I plus something times j, and that B is the same thing. How do we find the dot product of two vectors given in the component form? And you can show that this definition here of the dot product implies that if we know the components of A and B, then A dot B is the product of the components along x, y, and z added together. I won't go to the trouble to prove that now, but it can be very easily done. And so, depending on the way that the vectors are given to us, it might be easier in one case to use the upper definition. In some other cases, it might be easier to use the lower definition. So, that's how we take the dot product. And let me do an example, very simple example. But put it in the context of a physics problem. Find the work done by a constant force F acting on an object undergoing a displacement delta r, where the initial and the final position vectors are given here. And it says that we should assume that r is given in meters and the force is given so that those values 5 and 6 have units of newtons. So how do we do this? Well, we go back to the definition of the work being F dot delta r, where delta r is the displacement vector. We see, of course, that this is a constant force. And so we can just use the equation that holds true for a constant force. And what's important, though, is that we find delta r. And delta r is r2 minus r1. And so if we use the component method for doing that, 5 minus 3 is 2. So 2i. 8 minus a negative 2 is 10. 2i plus 10j gives us the displacement vector that takes the object from its initial to its final location. So now we just do W, the work is F dot delta r. We take the dot product of F and the dot product of delta r, and it's just the products of the components. So it's 5 times 2, those are the x components, plus 6 times 10. So we get 10 plus 60, which is 70. And the units of work, if force is in newtons and displacement is in meters, are newton meters or joules. So that's how much work is done. Let me close with this not so simple example, because it shows you one specific case of how to find the area under a curve where the force indeed is changing. Okay, it's not constant, which makes the calculation simple, but it's changing. So let's assume that we have an object that's just undergoing a one-dimensional displacement, because that makes it simpler, where the force is given by a function that depends on position, right? So as the object moves along the x-axis, if the x-coordinate is increasing, the force is also increasing. I'm not sure what would cause that kind of a force, but we'll just use that as an example. So the object starts at position x1 equals 3 and ends at position x2 equals 5. So it just moves from 3 to 5 along the x-axis, but as it does so, it's acted upon by this force. So what's the work done by this changing force? And we're going to go back to our integral calculus equation. So we write the work down as this funny integral sign. It looks like a very long thin S, and it actually does mean sum, as I said. So we're going to integrate the function f of x, and the dx reminds us that we're integrating, we're doing this along the x direction, as the object moves along the x direction from 3 to 5. So how do we do this? What's the rule when you have a simple polynomial type of function like the one given here? So we substitute for that f, 5x, and so this is the quantity that we're trying to evaluate. What is the area under the curve f equals 5x between x equals 3 and x equals 5? And since that function is a linear function, it actually is something that we could do without needing to use the calculus, but this will illustrate the method that works generally for all cases where the function is just something that is raised, where x is raised to a power. So here's the technique. The general rule is like this. If we have a function that is a constant times x to the nth power, and we're trying to find the area underneath that, between x1 and x2, we do something first that's called taking the antiderivative. Remember, when we take the derivative, the n comes down in front, and we end up raising x to the n minus 1 power. That is the derivative, which represents the slope. Here we're going in the opposite direction. It turns out that the area is given by the expression that we get if we raise the power of x by 1. So we go up, x goes up to n plus 1. The a is still there, but then we divide by this new exponent, n plus 1. So the antiderivative of ax to the n is ax to the n plus 1 over n plus 1. And the two limits of x1 and x2 are indicated here outside the brackets. Now what does that mean? Well, I'll show you in the next step. It means we evaluate this expression inside the brackets for x equal to x2, and then we subtract off what we get when we evaluate it at x equals x1. So the a over n plus 1 is a constant. It comes outside, and we plug in x equals x2, so that becomes x2 to the n plus 1, and then we subtract what we get when we evaluate x equals x1. So this simple expression gives us the general equation for how to find the area under a simple polynomial function graph. So back to our example, we had in the last slide this integral from 3 to 5 of 5x dx. So what do? X goes up to a power 2. So x was 1, x was to the first power, it's now to the second power, but we divide by the power. So it becomes 5x squared over 2, evaluated from x equals 3 to 5. So we have the 5 halves outside, we plug in x equals 5, which is 5 squared. Then we subtract off what we get when we plug in x equals 3, which is 3 squared. So 5 squared minus 3 squared is 4 squared, which is 16. 5 times 16 over 2 is 40. And once again, the units are in joules. So that is the general way of calculating the work done as the area underneath a force graph when the force graph is changing. That's all I have right now. We'll go on and show what good it is to calculate work when we introduce something called the work energy theorem, and that will be in our next class.